right, let's take a look at HSS-CP.A.3. The previous objective talked about independence. We continue with that. Here's where we start to introduce conditional probability. The idea of something having taken place and how it affects it. The classic, of course, is the non-replacement clause, that someone pulled a marble out, it's gone, and now we're going back in and the probabilities have all changed in the bag. So this is still about independence, but we're now going to look at independence dealing with the conditional statements. The idea of replacement, non-replacement, the idea of something impacting the next thing in the chain. Or not impacting it, because then it would be independent. Here's some new notation here. This says the probability of A given B. This line means given that B has occurred. So this means what's the chances of A happening knowing that B just happened? Now, if that equals the original probability of A, B did nothing to it. That would mean independence. This says the probability of B given that A has occurred is equal to the probability of B. What that means is it didn't matter if A happened or not. It just happened, and who cares? The probability didn't change. So this is a second test of independence. And these two tests are critical understanding in what we're about in this area of objectives. So connecting things, obviously independence, we're going to connect it soon to the probability of two events happening, sometimes being independent, sometimes not being independent. Lots of symbols here. Independence seems to be a foggy thing. My reflections are Venn diagramming unlocks. So let me give you just an example of what I mean by that. So here is a Venn diagram with the probability of A and the probability of B happening. Now the probability of A given B has happened is this part. Watch. What's the chances of A given that B has just occurred? So, well, B has occurred, so all of these things here in A are no longer possible. The only way to get an A value now is here in the intersection, because that's the shared probabilities of A and B. So given that B's happened, what's the chances of A happening given that B has happened? If that probability of the intersection, A and B, divided by the probability of B, if that probability is still just the probability of A, bam, independent.